Okay, my friends, shocker du jour. If I asked you who was the biggest big shot in physics, well, who would you point to? Everybody would say, well, Einstein. Well, what did he do for physics? He changed everything. He gave light a speed limit, which literally destroyed physics. He's the one that destroyed physics. He didn't make physics great, he destroyed it. I'll show you right now. Okay, my friends, this is a bit shocking. How fast does light travel? The speed of light from space.com, exactly 299,792,458 meters per second. Well, that's exactly, but this is through a vacuum. Nothing to suppress the light. It just takes off and keeps going. Well, first of all, there is no vacuum anywhere, and they agree with that. Right here, as a matter of fact, is Fermilab, and it says, empty space isn't empty. All right, and if you read this down here, it says that the foam on the head of a root beer is complicated environment, bubbles appearing and disappearing in a dizzying display of change. Empty space experiences similar activity because subatomic particles winking in and out of existence. These particles, subatomic particles, are real and have a measurable impact on the universe. So there is no vacuum, first of all. So when they look off into space and they say, we're so and such a distance away because the light coming at us never slows down, that is just not correct. And when they say the universe is expanding, it could be, but it's not necessarily why the redshift happens. Redshift just makes it slow down. I'm going to show you pictures of all this. And we have the pictures, and these are the things they refuse to examine. Now, these are not old papers. These are just a couple of days ago. Speed of light in the Britannica. All this light is fast, and the only thing that can reach this universal speed limit, the universal speed, no, it's not. You go faster than that. Here's one from February just this year. Why is the speed of light a random finite number? I don't know, some of them must be starting to understand, but they're all talking about this exact same number, and it's Einstein's law, basically. He destroyed science for 100 years. He seems like a nice guy, but his law, his demand, and there's a whole batch of laws, they're just all wrong because nobody understood, and they all had to base their situation on the speed of light being constant, and light being, nobody even knew what it was. They just thought, it's got to go the same speed forever. They didn't even know what it was. Wave, particle, that's what's called a duality. I show all this stuff in the experiments. All right, let's just start here. They're breaking light speed. They've seen it happen. They just can't understand how it could happen based on Einstein's demand that light doesn't speed up. All right, so this is just out today. In an amazing phenomena of quantum physics known as tunneling, that means going through the Venturi, particles appear to move faster than the speed of light. They don't appear to, they are moving faster. They're accelerating, let me put it that way, because there is no speed of light. Speed of light that's just a number that somebody forced on everybody else who was Einstein. So, however, physicists from Darmstadt believe that the time it takes for particles to tunnel has been measured incorrectly. So now they say, well, we got to figure it out because they weren't taking into the account the Venturi or this or that. There's some nonsense. If you can't see our particles accelerate, you got a problem with your eyeballs. All right, this is our stuff. This is what light looks like just before it starts to accelerate. This is a pulsar laser just going through the air. Now, I know the air can slow, anything, a medium can slow light down. Everybody knows that. Speeding it up, that's the thing they can't explain. How can it travel faster than this speed? Because this is the speed it travels in this medium, so that's case closed. It shouldn't go any faster than that. Well, guess what? She's a go very fast. All right, this is accelerating, and the reason is because of the tunneling. Well, what does tunneling mean? This is tunneling. They use a little Venturi and they say, well, and I don't think I've ever seen them show any pictures whatsoever. This is real pictures from a Samsung Galaxy S3 phone. This goes back to like 2013 or 2014, somewhere around there. And Rod Warren did this just accidentally, trying to make a double slit experiment. And he used nails, round nails, and tried to go right between them, and it created a venturi. And that's where it explodes, trying to get through the venturi. The white separates from the black, which is fission and fusion. And here it is right here. This is it right here. I just showed you. Light comes through before it accelerates. Okay, non-accelerated. All right. Then it hits, this is where it's just starting to accelerate. Now it's accelerating like crazy. And because of this explosion at the venturi, it's pushing back and making all of these particles light up. Because they're there, you just can't see them because they're not being bashed into. Normally they're going to bounce off a wall. That's when you see them. These are bouncing off of each other because they're exploding outwards so violently. All right, so we've seen here's before it accelerates. Here is it accelerating. Here is it as it divides. The black divides from the white. That's the venturi right there. And then they come back together right here. You see the size of those balls? They're all exactly the same. They're fixed particles. Now you see them, they look different sizes, they are not. The only reason you can see them is they're on top of the white, blocking the white from coming out. They're all over here too. You can just barely see them here. But they're everywhere. The black particles are just like the white particles. They're everywhere. Everything there is a dipole. And this was from my paper in 1970. Some of my final comments were the transfer of energy is from light, which is this, to atomic vapor, which is that. And I did a lot of work on this. I did as much as Einstein did, I'm sure, or more. This was my final papers about the speed of light and about particles. They were all dipoles. There's a lot of calculations, a lot of all this, and I showed my professors that this is all wrong. Everything was dipoles. Dipole interactions. Molecular dipoles, dipole moments. So two types, dipole interactions. And I got manuals coming out of my ears on this. I did this, like I say, nobody did it any deeper than I did it, because I went into everything, thermodynamics, chemistry, light, electricity, space, the whole 9 yards. And you can easily accelerate light. We just did, there it is right there. And this is the fission because it broke apart, and here's fusion where it came back together. And this is what the particle looks like. And the same thing, CERN knows this. Fermilab knows this. These are the two particles. They know it. And here they are, we found them. The reason they never find them is because they're smashing huge things together. We're using this. We're right here with light. Two particles back to back. That's it. They're hitting these things together, billions of them at a time, and just get an explosion. Then they dig through and they see what they can find. And they do find these at the two smallest particles, yes. This is from Fermilab. I didn't make that. Fermilab fixed particle and point particle. The point particle is that one. The fixed particle is that one. Never changes. The white ones can squish down and shoot right through the venturi. All right, almost all the schools I went to in the last 10, 15 years were through Coursera. And I went to many, many different schools. And you can go in and it's free. And these are all the communications I had back and forth. You can ask them questions about light particle research, human DNA testing, fiduciary failure of education, which is, it's a fiduciary failure. They are supposed to be acting in the best interest of the students, and they're not. And so they sort of put me to the side, but I still, you can go here for free. You can get all of these, and they send you what you're interested in. Take a look at this. Here's a new course coming out. And I took a ton of them. All right, so I went to a ton of courses from Coursera. And I went to the University of Geneva for particle physics, and Rice for chemistry, and a whole slew of them, because they were free. You didn't even have to take tests or anything. You just go there and listen to what they had to say. 99% of the time, I was in opposition to them, and every time I did say something, they just stopped talking to me. Now, this is Yale, and this guy, I like this guy. I'm not putting him down because he's being honest. He's at least being honest. These people are coming in paying thousands and thousands and thousands of dollars. He tells them, he says, we don't know what we're doing. Listen to this.
So this is a very exciting day for me, because today we're going to start quantum mechanics, and that's all we'll do till the end of the term. Now, I got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively, and the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys, because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now I am the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else. That's the only legacy a teacher can want. So,
I mean, he's being cute, but he's right. They're not going to be able to ask him questions he's going to be able to answer. He has no answers. Nobody understood it, because you have to understand the dipole nature of the particles, and that the protons are not made up of one big gigantic thing that has a couple of quarks and so forth in it. They're made up of all the little dipoles, and there's 1823 or so that make up a proton, and I believe 1824, the even number, makes up a neutron. Neutron means it's neutral, it doesn't want any more, it doesn't want to give any away. A proton is a charged particle. It either wants to take one more in to become stable, or it wants to give one up, and they share. All right, so they realize they don't know what they're doing, and they're correct. All right, basically summing it up, this is the particle moving through as a wave, because the particle's there, it has a magnetic field around it, and it has to push every other particle's magnetic field, and every particle has them, to get out of the way. That's why it has all these little glowy fields in front of it, because this big field is coming through fast. Pushing these, they glow, it glows much more. Now, as it approaches the Venturi, which is here, which is the nozzle, basically, they call it tunneling. Well, we're already tunneling out here, because this is what makes it accelerate. They're saying then the particle gets lost in there, so we don't know how fast it's going. Well, I can tell you right now, that particle has accelerated. If you can't see that, you got serious issues, and you should get to an ophthalmologist quickly. That thing there is going a certain speed, and now it's accelerating. There's just no question about it. It's zero. And when it comes out the other side, it makes these Higgs fields. They've seen these too, and they have no idea where they come from, because they smash everything to bits. And these are the particles they also see, again, have no idea where they come from. Those are the photons. And these ones here are the neutrinos. They're not quite up to the same strength as the photons. And the reason is these aren't in a direct line with the Venturi. Can I show that? Yes, I can. All right, here they are right here. When they're in a direct line with the Venturi, they accelerate and they speed up like crazy. The ones around here, you don't even see them. They're just because they're not being accelerated and they're not being pushed back at hard enough. When they hit up here, they're still in the air, just like light. You don't see light. You don't see this coming through the air. The only reason you see it is because it's accelerating. But these now are being pushed back at so violently, they glow like crazy too. And you can see back here, you see the waves going backwards? That's from this explosion. Incredible explosion. All right, and these are all the same particles. Here's the red ones again. Here's in the neutrino phase, they're just starting to get some energy. And then they start to stack up on themselves, and they just look like this, and then they hit the Venturi and they explode. And the reason it's only this one row right here is because that's the one that's right in line with the Venturi. And the same thing with the green right here. Here's the green, same particle, no difference whatsoever. And here's the neutrino phases. And this one's just getting ready to flip. The front one will charge up. And as soon as it gets charged up enough, whoop, it flips in it, and then the top one comes up and starts to absorb. You see? The red one, I can show you that happening actually. Where is it? Right here. And oh, by the way, these are the Fermilab particles. I think I showed you these. Just look it up, Fermilab point particles. This is exactly what I showed. The black one has all the mass, the white one doesn't. The white is small and big. It can get big and small depending upon how much impact it's having with its neighbors. This one's getting smashed, and it's getting, sooner or later it'll go, and that one will go in the front. That's called an upspin, that's called a downspin. And this is the particle in the black and white. And here's when it splits. Here's the accelerator. And here's what CERN says. They say these are muon neutrinos and electron neutrinos. I agree 100%. The black is the muon neutrino, and it stays a muon, sterile. The white turns into an electron shower. No question whatsoever, they're correct. But they just don't have any idea what they're doing because they started out way too big. We started with this. We started with this. So we can't get these big globs. And plus, they had to upgrade CERN to be able to use complementary metal oxide silicates, which is that's what we used. And they said, well, I did go to University of Geneva for particle physics, and I talked to them about it. I said, we can see these particles using CMOS. And they said, no, you'll destroy the CMOS. And I said, no, you destroy the CMOS because when you hit yours, you go jobs like that smashing into this, and it destroys it. When we hit ours, we're only using these, so it's made for these. Totally different thing. This is like throwing a hand grenade. All right, we're shooting a little BB gun. Smidge difference. They did go ahead and upgrade CERN, though, to be honest with you, to do exactly what we're doing with the CMOS. Because here's what they're doing. They're hitting these particles, big things like this, huge. And inside of each one of these is 1,823 or 1,824 little particles. It's not just a couple of things here and there. When they see these things all coming off, X means a chunk. All the rest of them are little bits and pieces of the light particles. And they see the photons. They just don't know what they do. They see them little, not energetic much. And then they see other ones very energetic. But they started out with these huge particles, smashing them together. And they dig through 10 years they dig through to find these particles. I'm serious. I'm not kidding you. Hundreds and hundreds of people searching through this until they came up with the thing that Fermilab put out and said, yes, these are the smallest particles we can find, which are these two particles. And yes, I agree. But we started with light. So we're already down where they want to get to. But we're starting with this. I don't think it's the right way to do it. All right, so you know photons are photons. The red and the green are exactly the same. And the red is just very slow. It doesn't have that zip. The green is coming through here, smashing into the red, just pushing it out of the way, and then reconcussing way out here. So the green is extremely more powerful, and the blue is extremely more powerful than that. When it comes through the Venturi, you can't even tell there's two particles attached together. By the time it gets out here and slows down, you can see that there is two particles attached. So there's light slowing down after coming through the Venturi. I showed you light speeding up. Of that, there is no doubt. Okay, and I showed you the light splitting. I showed you the particle spinning. Well, maybe I didn't, but well, this shows you the spinning. It slows down. As it slows down, it drifts to the left. It's spinning to the right, and it will drift to the left. Because that one shot is all that one thing all at once. These are their Higgs fields. These fields like this, but they're just making huge, gigantic jobs in blast. We could see the Higgs fields in absolute magnificence. Look at them. Look at that. That's where that white is coming through all by itself. The black stayed back. This is when the black reattaches to the white. That's when the fields show up. You see this one hooking back in it together, and it's turning into a field. Once they hit the black, they start spinning like crazy. And all of these are doing the same thing. And here's another one from CERN. They show this event, and that's a big deal to them. Well, the reason the blue goes and never comes back is because it's right tight. I don't think I showed you this. This is dipole electron flood theory. This is on the internet. It's called dipoleelectronflood.com. Come up here and look, and these are the way I claim the proton is made up. So the black all goes to the center, and the white all carusts around it. All right, and there's 1,823 dipoles make up the proton. But way deep inside is the black. And all the whites go to the outside. So we never have seen the dark matter. That's why, because it's always inside. It's everything. All this stuff contains dark matter. Everything you see contains dark matter. Even light contains dark matter, because this is it. This is the light part of light. This is the dark matter part of light. And that's also gravity. That's what causes gravity. And these two together, put like this, is what we would call an electron, or a gluon they call them now. And then you have the photons, which are two gluons back to back. This is not stable. It will burn or incorporate as heat. This will bounce because it has a field completely surrounding it. And there's going to be some changes to science, chemistry, the redshift space, distances that they measure, and also isotopes and all of the periodic chart's going to have to change too, because hydrogen is not one proton and one electron. It's about 1,825 or so dipoles in a ball like that. And you hit that with one little spark and everything goes, because they're held pretty loosely. And that's why hydrogen is so, it's in everything. Hydrogen is the most, is the top particle in the universe. All right, there's more hydrogen than there is anything. And the reason is it can get in and out of other particles very easily because it's very small. And biologically, it's magnificent, actually. All right, this is not simply about breaking the speed of light and creating a venturi. This is possibly about getting free energy. Now, why I say that is because of this. This is high energy showers, high energy showers. These are low energy showers. What does that mean? It means it increased energy. All right, and that's exactly what happens at the venturi. The muons back off. You see this right here? These are muons. They back off. The electrons from the electron showers come through and they create huge showers, which is exactly, precisely what I showed you through our venturi. Now, what does that mean? You have to harvest this at its peak. When you get the most showers, then you're going to be able to receive those particles as literally electricity. And they'll flow right down into your battery or whatever you want to use it for. And all you have to do is shoot red laser through a venturi. Or not red laser, you want a higher energy laser. There's a lot of work to do on the engineering side, but it's not that hard. This is not me. This is not my stuff. I didn't make this. This is, I think, Lawrence Livermore. I'm not certain of that. That was one of the big collider places. They understand this. Electron showers are what you want. You want high energy electron showers. Electron showers. Precisely. Exactly what I showed you right here. The muons stay out, just like the Lawrence Livermore shows. They just stay out of the picture. The white ones turn into the showers. Harvest it there, and we might be able to walk around with a little lunchbox to drive everything in our whole lives. Whoops. Something like this. You have all your different outlets in here, all your different styles of electricity, anything you want, USB, and all of the laser would be very, very simple to power. You just tap off some of this. Because if you increase from low energy to high energy, that means you have excess. Now, this should be looked at. There's no question. And it's been refused for 10 years now. I mean, refused. I've tried everybody. And I've shown them all the same things I just showed you, all of this stuff. And I said, well, what about Fermilab? Fermilab is saying this stuff is real. All right, Fermilab. That's their work, exactly the same as mine, identical. And it says the same thing. The black one has all the weight, extended particle, a fixed size, never changes. It has a fuzzy edge around it, the color, yes. And a point-like particle has zero size, no weight to it to speak of, but it has a field. And then they also go into the same thing I talk about, this the quantum foam. These light particles are particles. They're actual physical particles. When they come from the sun, they don't just go nowhere. They're in space. They're everywhere. Everywhere there's light, they are there. And there is light everywhere. All right, so that leaves me with a couple final statements. First of all, how would you like to be paying for your kid to go for physics and find out that everything he's learning is, or she or whoever, is just not correct? And they know it's not correct. It's not a question of not knowing. It's a question of not caring whether it's correct or not. Otherwise, this would have been looked at long ago. And that's the problem. So the fiduciary duty of everyone, especially teachers, is to look out for their students' interests, not to look out for their own interests. And that's all I've seen so far, is self-interest in academia. And this is not a good situation. So if anybody can come up with an objection to what I showed being reality, I'd like to hear about it. But in the meantime, I'd love to see this pursued, and we can get some free energy maybe. How about that? It's free, clean, cheap, or cheap, almost free. Once you get this going, I don't see any reason it should ever shut down. It's all solid state. You're just shooting laser through a Venturi. You don't have to add any energy whatsoever. It breaks it apart, and you get the high energy showers automatically from these little particles. Harvest them way up here, and you got high energy. All right, so it depends on how many lasers you have in here, but you could put thousands and thousands of these tiny little lasers in here with the photo receiver right on the other side of it, because it's so tiny, it's just amazing. And then you put it into what they call a bus, which is a bus bar, and they all go into the filter into that and down into your batteries or wherever you want to store that energy, or just turn it right on and use it. And I think you get a hell of a lot of energy out of something that size, I'm pretty sure. But that's it for today. Thank you. Speak up. These kids are being taken advantage of in every realm of science, in every single realm. History, geology, physics, you can see. Chemistry's got to change. Anthropology. History is just absolutely crazy. They have to take into account all the things that were written that they just made everybody laugh at. And if you speak about it, they fail you. This is the problem with education now. It's got to change. It has to absolutely change very, very quickly. And you're the only ones that can do it. I've tried for 10 years now, more than that. I've gotten zero, almost nowhere. And my channel is just about dried up. It's like the Sahara Desert now. Only I don't have a dragon on it. What a world. All right, I love you all. Bye.